Hello, everyone. Welcome to our live session for, what is this, Wednesday, September 7th. And we are dispersed today. My name is Matthew. I'm one of the course staff for our online classes, and I work at Steward Observatory. And thank you all for joining us today. We have our normal practice here today is that anybody who's on with us can post questions in the chat, and we will grab your questions from the chat, and then I will pick those questions and then read them to Professor Impey, and then he will answer those. And so we try to go generally in order, but I jump around so to give more people a chance to choose or to get a chance to ask a question and to pick a variety of topics. So Chris, do you want to just give an introduction and we'll get right into questions?
Sure. So welcome everyone to the online live Q&A session for our massive open online classes, or however else you might have found this session. And we have a lot of repeat customers, I know. I'm coming to you today, this afternoon, actually, in Europe, from northern Italy, from Bellagio. If you've ever been there, it's gorgeous. It's on the shore of Lake Como in northern Italy, near the Alps, and it's an amazing place. I'm at the Rockefeller Foundation's center here. George Clooney has a house just across the lake, and other celebrities. So it's kind of a rarefied place full of rich people and great food and wine, of course. So, but that's not why we're here. The floor is now open for your questions on astronomy.
Excellent. The very first question is from an email. Ravi asks, I'd like to ask if you think that Fritz Zwicky is underappreciated in the world of astronomy. He made many landmark contributions, but so far, I don't know of any institutes, observatories, or space missions named for him. Can you talk a little bit about that?
It's a great question. He is a little bit an unsung hero. Most professional astronomers are very well aware of his contributions, and so he's held in great esteem within the field of astronomy. He's a famous astronomer, no doubt about it. But yes, he's not heralded beyond that. He doesn't have, as you say, institutes or space missions named after him. He's had a few surveys named after him, I think. That's about the level of his fame. So Zwicky spent most of his career at Caltech, and he made seminal contributions to a number of subjects in astronomy. He was really ahead of his time in many ways. Probably the most famous thing he did, but by far not the only, is he anticipated dark matter. He had a very influential paper in 1933, which looked at the velocities of galaxies in the Coma cluster and recognized that the range of velocities, radial velocities of those galaxies indicated far too much mass to be accounted for by the visible galaxies. In other words, the motions of galaxies in a bound system should be driven by the gravity or the total mass of the system, and the visible galaxies should not have been driving the velocities dispersion or range of 1,000 kilometers per second within the cluster. So he used that to infer the presence of dark mass holding the cluster together. And remember, this is 1933. This is only 4 years after Hubble found the Hubble relation, the relationship between radial velocity and distance. So this is very early days in extragalactic astronomy. It really didn't get followed up very quickly after that. It was decades before dark matter became a ubiquitous part of the astronomical landscape. He also made very important contributions to the theory and observation of supernovae and other transient events in cosmology. And I think I can venture, at least without casting aspersions on his reputation or character, one reason why he's not as famous as he might be. He was an extremely prickly, persnickety, crusty, cantankerous type of individual. That's very clear. And I was a Caltech postdoc, so I talked to people who worked with him late in his career. So he was just difficult to deal with in many ways. So sometimes that affects how your reputation comes down through the ages.
Excellent, thank you. The next question is from, one of our live participants. Yangip says, hello, Professor Impey. How many possible dimensions are between de Sitter and anti-de Sitter space? Is there any transitory methods in spatial morphologies?
They're distinct concoctions, if you like, or formulations of space-time. De Sitter space was named, just to back up a little to the context for this. De Sitter was named after Wilhelm de Sitter, a German cosmologist from early in the 20th century. He was a contemporary of Einstein and Minkowski and other people who worked on space-time and the expanding universe. So he's a theorist. And he formulated in the model of general relativity, which had only just been published, the idea of a sort of empty expanding space-time. So de Sitter space-time is typically empty. It doesn't have matter in it. And you can indeed formulate, anti-de Sitter space-times, which you can have contracting or expanding space-times. These are very artificial models because we, of course, live in a universe that has matter and radiation. So nobody really thinks de Sitter space in any regard is describing the universe we live in. But it's a useful limiting case, if you like, of an empty universe where you're observing the space-time behavior directly without the influence of matter or radiation.
Excellent. The next question is from an email. Lucy is interested in calendars and says, while the Gregorian reformation of the Julian calendar took us to the closest to the time it takes the Earth to orbit the sun, I think that this can be improved upon. He has some ideas, but generally, can you talk about why we use the calendar system and why there aren't any better, more accurate options available?
So the calendar, use of calendars in human culture going back thousands of years is trying to resolve civic life, the life we live in our daily lives in an agricultural or industrial society, and astronomical time. So astronomical time is based on the orbit, the spin of the Earth, which defines the day, and the orbit of the Earth around the sun. And of course, it turns out that for the Earth to go exactly one orbit around the sun is not a round number of spins of the Earth. So the number of days in a year is 365.24199, and I forget the decimals after that. And calendars are an approximation to try and get as close as you can in counting days to match that year, the time in an orbit. 365.24 and a little bit is a little less than 365 and a quarter. And so a simple 365-day calendar plus a leap year gets you to 365 and a quarter. And that's 100th of a day off. And that was the Julian calendar. And after 1,000 or so years, that 100th of a day per year had accumulated to almost 2 weeks. And that's why the Gregorian calendar was developed. It added a rule of divisible by 4 years, every 400 years, to make it slightly closer to the true time of an orbit. And it's pretty good. That calendar only loses a day in centuries, maybe a millennium. It's not perfect though. And the question is right, that there could be a better calendar, even better than the Gregorian calendar. But really for civic life, it's not necessary. The world, first of all, the accuracy of our measurement of time based on gyroscopes, GPS, and so on, and inertial reference systems beyond the Earth means that we can see the changing of the length of a day from 1 year to the next because of variations in the Earth's orbit. So we're measuring subtleties of time that are just as big as the problem of our calendar in the Gregorian system. So I think the truth is, yes, we could have a better calendar. It would be easy to devise one that would not go off for 1 million years, say. But we don't notice it. In civic life, the calendar we have is actually pretty good. And so the Gregorian calendar was a really important innovation because it gave a modern industrial society a calendar that's been good enough.
Excellent. That's really interesting. I don't think we've had a calendar question on here before. Ayup Ardra, who's on with us live, says, hello, Professor. I hope you're well. My question is, we know that each carbon atom is unique. That's why life on Earth is based on carbon. I wonder if life on another exoplanet could be based on different things other than carbon.
So the speculation about life in the universe and whether it might have a different basis than our life is widespread and has been going for decades, even as we still don't know of any other place with life. Chemists and biochemists have weighed in on this subject. Carbon is unrivaled in its ability to make stable long chain molecules and to combine with hydrogen and oxygen to make hydrocarbons, the basis of molecular life, and to build complexity in a biological organism. It's unrivaled in the sense that there's no better simple atom that can do this job. If you go vertically in the periodic table, you get to silicon. And so some people have speculated about silicon life, which has somewhat similar chemical properties. But silicon is not the same as carbon. And in lab experiments and theoretically, it does not form as many or as robust molecules. So as a basis for biochemistry, it's not as good. Now, it's possible in the universe, in all of the experimentation that occurred chemically that may have led to biology, that there might be silicon forms of life. But biologists and chemists tend to think that that's not going to be a route that life would take in general. So it's not to say that carbon is the only possible basis for life. Maybe there are other ways you can structure molecules to store information, and we need to use our imaginations a bit more. But carbon is one of the most abundant elements in the universe, created by stars after hydrogen and helium. And so it's abundant, it's available, it forms complex molecules easily and readily, and that's why people expect life beyond Earth to be based on carbon.
The next question is from Lawrence 4040. Professor, how does Hawking radiation escape from a black hole? Is this how black holes evaporate? And is this how information is preserved?
Yes, Hawking radiation is a mechanism hypothesized by Stephen Hawking in the late 70s, early 1980s, whereby black holes have another property beyond mass, angular momentum, and size. Those are the simple black hole properties. They have temperature. This temperature for a stellar mass black hole is billionths of a Kelvin, so it's an incredibly small temperature. The radiation results from the creation from virtual pairs of particles and antiparticles that come and go out of the vacuum. This happens routinely. We see it in the lab. We can simulate this, and it will happen in space near the event horizon of a black hole. And at that point, it's possible that one member of the virtual pair will escape the black hole and one member of that pair will go in. And so that separation leads to a net loss of mass, and since E equals mc squared, a net loss of radiation or emission of radiation. The question of where this energy comes from is it comes from the vacuum. I mean, it's borrowed energy from the vacuum of space, but it's lost to the black hole. And so that's the cause of Hawking radiation, and it means black holes evaporate as they shine with this very low temperature. It's a theory so far. It's not been verified, and it may be very difficult, perhaps even impossible for astronomers to show that black holes have a temperature and that they do evaporate.
The next question is from an email. Kathy Donnelly asks, do you know how many Starlink satellites there will be in total in the final constellation? And can you talk about the effects of the Starlink satellites on astronomy?
Yeah, so the last projections I've seen are numbers like 40 to 42,000 Starlink satellites, an enormous number. And at the moment, we're only at a few thousand. The number's increasing very steadily. So that's an enormous number of low Earth orbit satellites. On its own, that one project will triple the number of low Earth orbit satellites when it finishes launching these within only a couple of years. It's of concern to astronomers because these satellites do have reflective properties. And so when sunlight's incident on them, that sunlight bounces down to the Earth, and astronomers can see, especially at twilight, at evening and morning twilight, these satellites light up. And we've already seen at major observatories in the United States and in Chile, the starlight tracks, the trails of these satellites streaking across deep sky images, and that's only going to get worse. So this is a matter of real concern. SpaceX Elon Musk has got his company to experiment with different coatings, with more absorptive coatings, so these satellites don't reflect as much radiation, but they have some reflection anyway, and they're also in pretty low Earth orbit, so they're quite close to the Earth. The only saving grace of the Starlink satellites is they will not be up there forever, causing collisions and increasing the amount of space junk. They're in a low enough orbit that they will naturally degrade the orbit over time due to very slight drag with the upper atmosphere, and they will gradually deorbit, and of course then have to be replaced. So they won't be there forever.
The next question is from Isla137. Hello, Professor. My question is, what does gravitational lensing, or why does gravitational lensing give an odd number of images around the massive object?
So gravitational lensing is a consequence of general relativity and the curvature of space-time. And the way to think about it is in terms of the theorem that says that light will take the minimum path, the minimum time to go from two different points, from point A to point B. And when space-time is curved, that minimum time path can have multiple solutions because you have a curved surface. And so the light travel time can have multiple solutions, not just a single solution. And so if you want to think of space-time as curved, then just imagine a fold in the light path time for light traveling through curved space. And each time you make a fold, you add two intersections with a light beam. And that's why you start with one image, this the undisturbed image with flat space-time. And as you add a fold in space-time caused by space-time curvature, you add images in pairs, two at a time. If you had a second fold, you'd add two more and have 5 images, and then 7 and 9. And so it's always an odd number of images. And in fact, in some gravitational lensing situations, I think the record now is 13 images have been seen of a single object in a gravitational lensing situation with complex curvature.
The next question is from Vedant Mana. Good evening, sir. I'm from India, and I'm interested in astroinformatics. Can you talk about data science in astronomy and how it can help us?
Well, astronomy is in the vanguard of the movement in science, which goes across all science fields of big data. So astronomy is a big data field. Many fields of science now involve big data. Probably the most notable example is in biology, genomics. So as we parse the information in the human genome or in other genomes, and as we solve the problems of protein folding and understand biology at a deeper level, you're involving huge amounts of data. Astronomy has big data for two reasons. One, because the instruments, the detectors, the CCDs are now very large. They have tens or hundreds of millions of pixels. You're taking images quite frequently. And so the data rate at a large telescope, like the big one being built in Chile that will survey the sky to Hubble depth every 3 days, is about 20 or 30 terabytes a night. So that's a pretty standard number now in big data astronomy. Astronomy also generates big data because we do simulations with supercomputers. So many things are simulated, from gravitational lensing to gravitational waves and gravitational radiation, to how we understand the distribution of stars and galaxies, to how we model an entire galaxy like the Milky Way in terms of its individual stars. These require trillions of computer operations, and the objects are moving by gravity. So you're storing data in time steps, and so it very quickly becomes big data. So astroinformatics is just a term that refers to the fact that astronomy is now resolutely in the regime of big data, and that's what astronomers almost always have to deal with now.
Next question is from an email. Stan Stachowiak asks, could you please discuss how the cosmic web formed, when, and is it related to dark matter?
So the phenomenon called the cosmic web it's a very evocative term, and you can actually see images of this. It's really most easily seen in simulations, but we have seen observational evidence that the cosmic web is a real thing. So if we think of the universe, this galaxy, most of the material, dark matter or visible material, is in the galaxies, and the intergalactic regions of space seem to be essentially empty. But they're not empty, because those intergalactic regions have dark matter too, and of course dark energy, but in particular dark matter. They also have a very thin, diffuse, and very high energy and hot gas called the intergalactic medium. That's at a temperature of hundreds of thousands of Kelvin. And so this medium, this very thin medium, develops structure as time goes by and gravity acts. and it tends to form this filamentary pattern that we would see as the cosmic web. These are filaments and sheets, and the intersection of sheets into lines and so on. So it has a dimensionality not like strings and not like sheets, but sort of in between. The dimensionality, if you do it as a fractal dimension, is 1.7. That's the cosmic web. And when you see a computer simulation, you're just seeing a visualization in the simulation of this very hot gas that lies between galaxies. So that's the cosmic web, and it evolved over billions of years after the Big Bang due to the action of gravity. The fact that the cosmic web exists has been verified because we've used, for example, X-ray telescopes to see that there is an intergalactic medium with that very hot temperature. We can see the glow of the cosmic web. Another way we've detected the cosmic web, and I've done some of this research myself in the past, is by using quasars as probes of the universe. So we use quasars as flashlights shining through large distances in the intergalactic medium. And where the sight line penetrates a node or a filament or a sheet in the cosmic web, there's an absorption due to hydrogen or helium, which is most of the gas is made of that. And so we can map out the cosmic web with these sort of one-dimensional sight lines through the universe. And if you have enough sight lines adjacent to each other, you can set up a grid of probes and actually see the three-dimensional structure. So the cosmic web has been mapped out. And it also shows that most of the baryonic material, that's the stuff we're made of, protons, neutrons, and electrons, exists in the space between galaxies and not in the galaxies themselves.
The next question is from Rentgen 101. Since you are in Italy, can you discuss contributions of Italian astronomers?
Certainly, Italian astronomy is very important. European astronomy is a major part of the research that goes on in the world. The Italians have been involved in astronomy, of course, since Galileo. So if we're talking about the full history of Italian astronomy, we say it's a 400-year history since Galileo was the first physical science scientist. He was the first to not use, but to perfect the telescope for astronomical observations. So they have a very long and very illustrious history. In the modern era, there have been some very famous Italian scientists. A number of them did their work in the United States, and the two dominant examples we could think of from the 20th century would be Enrico Fermi, who was a physicist, but he made contributions to astrophysics too, and Riccardo Giacconi, who was the director of the Space Telescope Science Institute and one of the architects of the Hubble Space Telescope. Both of those men won Nobel Prizes in physics. And there have been other famous Italian astronomers into the modern age. Italy is a member of the European Space Agency and also a member of the European Southern Observatory. So Italian astronomers get access to space missions through ESA and access to telescopes through ESO, which has most of its facilities in Chile. I'm not working with astronomers particularly in this trip, in this residency. It's more of a think tank on policy and so on, but I do know a number of Italian astronomers, and they've been very dominant in X-ray astronomy in particular.
The next question is from Hernan, who sent an email. With the world situation being what it is, the economy being sorely hit between the war in Ukraine and climate change, what do you think the chances are that missions like the forthcoming Europa Clipper and Titan Dragonfly will still be funded? I ask because at 71, I'd like to live long enough to see the results.
Well, I hope you do, Hernan, live long enough. I don't think these missions, those two in particular, those are outer solar system missions that are very exciting. They're follow-ups to the most interesting places we can study where there might be life, Europa and Titan, one a moon of Jupiter and the other moon of Saturn. These missions are still on the manifest, they're still on the table. They have initial funding to study them and concepts and designs and engineering studies. But of course, they're years away from being executed in terms of building the mission and launching it. And then it's, of course, a good part of a decade before it gets to its destination and the science starts coming back. So I think these missions will happen. They have high priority within NASA's forward look. When NASA does a 10-year strategic plan, those two missions remain in that plan. But the problem with NASA, of course, is a finite budget and a squeezed budget. The Artemis mission that's had its own hiccups in the last few months is extremely expensive. It's sort of back to the future for NASA with a rocket that uses technology that in the space shuttle was a very flaky technology involving liquid hydrogen. And it's very expensive. And so some of the rocket, some of the rocket development missions or science out of NASA is compromising the planetary science and the astrophysics, which is not leading to cancellation of those missions, but it's leading to their delayed timelines. It's not clear how much those missions will be delayed yet, but they probably will be delayed by the problems of Artemis.
Rosaline66 asks, good afternoon, Professor. Do you have an update on the James Webb Space Telescope, please? I've read what I can, but do you have any other information, or can you talk about its current status?
Sure. The James Webb is just doing its work now. It's in its early science phase. The instruments have all checked out. They've tested almost every mode of every instrument to make sure that they function normally. That took a while, took weeks actually. And they released some early science data, which everyone saw. But now, since then, it's basically just been working through its scientific observations. It's been doing deep field observations. It's been trying to spot galaxies at the dawn of time, and it's been doing more exoplanet work. And you probably saw just a week ago, it took the first image made of a hot Jupiter, actually, so a Jupiter-sized exoplanet in the infrared. And so it's we're seeing occasional science results from the James Webb, and we'll just see more as time goes by. It's doing some small projects, individual objects, and it's doing some large projects and usually surveys of areas where it has to sit and dwell and look very deep to find objects that are far away. There's been no hiccups or hitches in James Webb. The data is flowing smoothly. The instrument is performing nominally. The impacts from micrometeorites that people worried about, that's not happened again. So there's been no more damage to the mirror, and everyone's very happy with the mission.
Next question is about Artemis. Since you mentioned that, I thought it'd be a good time to bring that up. Can you talk a little bit about what's going wrong with Artemis, with the launch getting delayed? What's the deal?
So Artemis is there's a long history here, which I can only give in summary form. NASA has been searching for a deep space heavy launch capability ever since the retirement of the space shuttle, which is now 12 or 13 years ago. And as you probably know, for a decade, NASA could not launch American astronauts into Earth orbit without help from the Russians and the Soyuz. And now that we're very much on the outs with Russia, that's not available. And so it's SpaceX and Elon Musk that's leapt into the fray to get American astronauts into space. But all through that time, NASA was planning a successor to the space shuttle. But it's really a project that harks back to the days of Apollo and the Saturn V. It's an enormous rocket. It's huge, the biggest rocket NASA's ever built. It is the most powerful rocket. It's called the Space Launch System. So you'll see SLS, that acronym, out there. And it's a technology that, again, is 60 or 65 years old, and it has the Achilles heel, as we've seen in the recent delays of Artemis 1, that it involves the combustion of liquid hydrogen, and storing liquid hydrogen and preparing it for combustion in a rocket engine is extremely difficult. And so a hydrogen leak led to the last delay. But liquid hydrogen has been finicky through the days of the shuttle, and it's finicky now with the Space Launch System. When this issue is resolved, Artemis 1 will be a test launch that will go to the moon. Artemis 2, and it will be uncrewed. Artemis 2, about a year after that, will carry a crew to the moon, go around the moon and come back. And then Artemis 3, also about a year after that, will be the first return of American astronauts to the moon after an absence of over 50 years. NASA's already committed in writing and on their website to the fact that a woman and a woman of color will be among the crew that land on the moon in this mission. But in the meantime, there are technical problems because this is a finicky and fairly old technology that they're using.
So that brings up the question. So if hydrogen is so finicky, then why use it? Why not go with something more like what SpaceX is using?
Well, hydrogen is finicky, but it's also, when hydrogen combusts with oxygen and makes water, essentially as a byproduct, it does release energy very efficiently. So hydrogen is a very efficient fuel. The alternative fuels are essentially hydrocarbons, sort of very volatile versions of aviation fuel. And those fuels are also used in the space program. Most planetary probes use those kind of fuels. But when you want a lot of power, when you want a lot of impetus, a lot of specific energy, if you like, from a rocket, then burning a little hydrogen is a very efficient way to go. It's just very difficult to store it and keep it at the appropriate temperature, of course, under pressure, and deliver it through complex plumbing, essentially, to an engine that must combust at a ferocious rate to generate enough lift to pull this huge rocket off the ground.
The next question is from Lawrence 4040. Hi, Professor. Are observers in other galaxies closer to or further from the cosmological horizon, or are all galaxies, stars, planets equidistant from the cosmological horizon?
And that's a good question. And basically, due to the sort of cosmological principle, we have no special or privileged place with respect to the rest of the universe or the creation of the universe in the Big Bang. And so every observer in every galaxy has their own cosmological horizon. So in another galaxy or a distant galaxy, they will have a horizon that's also determined by the farthest they can see where light could reach them in the history of the universe since the Big Bang. And since that time, since the Big Bang, it's the same for everyone, the distance to the horizon is the same for an observer in a distant galaxy, but they're measuring it with reference to their position.
The next question is from Starsend1. Asks very literally, if a book falls into a black hole, will the information be lost? But can you talk more generally about what does it mean to lose information in a black hole?
Well, that's a good example to talk about a book falling into a black hole. Yes, if you toss an encyclopedia or book with information in it into a black hole, that information is not retrievable according to the laws of physics. And so that information is lost. And that's a very direct form of information loss. But it's also more generally true. Any form of matter, any organized form of matter, any physical object has information in the arrangement of its atoms and molecules, and that information will be lost when the object falls into the black hole. Radiation doesn't have, and photons don't carry information quite in the same way. They're really carrying entropy or disorder more. But you can generalize the idea of information to say that regardless of what falls into a black hole, that information is being lost. The question in black hole physics that's not yet resolved is whether that information is fully and truly and permanently lost or irrevocably lost, or whether it's somehow stored some way. And there's a theory called the holographic principle that suggests or supposes that the information that falls may be stored somehow, imprinted on the event horizon like a hologram at the event horizon itself. It's still lost because nothing at the event horizon can be extracted, but it avoids the issue of the information being lost forever and for everyone. It's just stored at the event horizon. But that theory has not been tested.
The next question is from one of our live participants, Pargade1. Hello, Professor. Is the formation of cell membranes and hence formation of a cell a critical step in the development of life on a planet? If so, is there any research on other ways to form cell membranes other than a lipid bilayer?
There is some lab research on how cells form, on the evolution that leads to a cell. And the ideas really haven't changed for the last few decades. And as the questioner suggests, the basic argument is that when there are fatty materials, fats essentially, in a chemical sense, dissolved in water, those fats can join together and form a lipid layer. And that is because some molecules are hydrophilic and some are hydrophobic. That is, some molecules are drawn to water and some molecules repel water. And so that means the layer is asymmetric. And there's a natural energy principle of minimum area that will lead layers of these molecules that may exist, for example, as sheets in a liquid, to naturally form into spherules or small spherical objects. And this has been simulated in the lab, and these little vesicles, as they're called, because they're not really cells, are much smaller than a modern cell in a single-celled organism, hundreds of times smaller actually. Well, but they have some of the same properties. They concentrate chemicals within them. They allow osmosis or passage of chemicals and molecules through the membrane and out of the membrane. And people view that as a really critical step in the development of life. But it's very different from forming a cell with all the apparatus in a cell. So these experiments have not connected the dots between simple chemicals and the first cells.
The next question is from David McKenzie, who sent an email. Good morning. I've been looking at data on the NASA Exoplanet Archive site and was wondering if you could explain the difference between ecliptic latitude and longitude versus galactic latitude and longitude.
Sure. So NASA keeps repositories of exoplanets, positions in the sky, and it could be any object that we have cataloged with positions where you want to observe it and point a telescope to it. So this could be exoplanets, it could be galaxies, it could be quasars, it could be any object except moving objects like solar system objects, so any distant object. Ecliptic latitude and longitude are a reference frame that exists relative to the spinning Earth. So this Earth spins, it has a tilt on its axis of 23.5 degrees. And so the sky rises and sets according to the spinning Earth. And ecliptic latitude and longitude just reference two angles in the sky relative to the spinning Earth. One is a sort of angle above and below the equatorial plane of the spinning Earth, and the other one is an azimuthal angle. So that's where ecliptic latitude and longitude come from. You can also do referencing to the Milky Way itself, which has its own plane, the plane of the Milky Way, and you can have latitude and longitude with respect to the Milky Way. And so people define Milky Way coordinates too.
The next question is from Gareth Harm, who is on with us live. Good morning, Professor. I've been reading in the lay press about the possibility that our understanding of how the universe formed with the Big Bang and that the universe may not be expanding after all, given all of the data coming from James Webb. Could you please comment on this?
So the questioning of the Big Bang and the suspicion that it may not be correct, or the final theory, that this happens episodically. You see stories about this every few months or every year or so. There's no critical flaw in the Big Bang. So I think most of these stories are either overblown or they've sort of misinterpreted something in the research literature. There are definitely flies in the ointment, if you like, to use that phrase. There are parts of the Big Bang model that are not completely holding together. Obviously, the big issue for us in astronomy is dark energy and dark matter. We don't know what they are physically or fundamentally. But the fact of the Big Bang as an early hot, dense state of the universe is not questioned in any profound way, because there's so much evidence that the universe has been evolving, and there's very direct observational evidence that it was smaller, hotter, and denser in the past. And that's all part of the Big Bang model. So I think the odds that the Big Bang model itself is fundamentally wrong are very low. But we know it's incomplete, and we know that there may be issues in the Big Bang that will involve, substantial changes to the theory.
The next question is from, let's see, one of our live participants. Planetary Terry asks, can electromagnetism be a part of, albeit small, force in the equation of accretion?
When accretion occurs in an astronomical setting, electromagnetism is relevant. So accretion typically occurs in a hot region surrounding a star. This could be an accretion disk around an individual star. And on a large scale, we have accretion disks that surround the black holes at the centers of galaxies. So accretion disks can be, star scale or very big scale in the center of a galaxy. In either case, they're very hot gas, so they're our plasma. So in a sense, there's not a lot of direct electromagnetic energy involved in an accretion disk because it's a plasma. The charged particles, the protons and the electrons are liberated from each other and they're moving freely. However, there is a magnetic field that entrains an accretion disk in all these situations. And so it is possible to get electromagnetic effects associated with the magnetic field that threads an accretion disk and the fact that it's twisting as the accretion disk rotates. And so you can generate electric fields from the magnetic fields. That's a standard thing that Faraday showed hundreds of years ago in the lab. And so, yes, there are electromagnetic effects, the dynamo effect, for example, that can occur in an accretion disk.
The next question is from one of our live participants, Vedant Mana asks, Sir, recently a picture came up where a white light spot was seen in a black hole. I'm not sure exactly what the picture is, but I see a recent story about a light being seen from behind a black hole, looks like from a gravitational lens. So perhaps you can talk a little bit about how that's possible.
Sure. This has been seen in a number of ways over the last years. So we have black holes in the centers of galaxies. These are typically quasars, and the curved space-time that occurs near a massive black hole can lead to a light behind the black hole bending around the black hole and then being imaged at a telescope that we can observe. So when you look towards the black hole, you're seeing the light spot, the light source behind the black hole, and you're also seeing probably multiple images from gravitational lensing. So these are the kind of artifacts we see. And then remember, they are artifacts. It's a mirage. There's really only one object there, but its light is being distorted and bent by the act of gravity.
Excellent. There was also a recent picture that showed what was being called an almost perfect Einstein ring. So I don't know if you saw that picture, but can you talk about what an Einstein ring is and what makes one perfect or less perfect?
Right. So Einstein rings have been around for decades, actually. First gravitational lensing was observed of a quasar was observed in 1979. The double quasar was actually first observed at the multiple mirror telescope at my observatory, Steward Observatory in Arizona. And I think the first Einstein ring was found a couple of years later in the early 1980s. So we've known of Einstein rings for 40 years. An Einstein ring is a situation where the alignment between the object and the lensing object, the object behind, and then the lensing object is perfect. And by symmetry, the bending of light forms a symmetric shape. And so if the light is being bent by equal angles at every azimuthal angle, then you end up with a circle. And so you have an image, you have a point source, light source, that's being turned into an image that's a ring just by the bending angle and the symmetry mapping it around 360 degrees. So the physics of that and the idea of that is actually quite simple. And it only occurs, you only get a full Einstein ring, uniform brightness all the way around when you have perfect alignment. If the alignment is slightly imperfect, slightly off-centered, then the Einstein ring symmetry is broken, and so you end up with arcs. So when the alignment is less than perfect, the ring breaks into arcs, and that's the more typical case because it's very rare to get a perfect alignment. I think there are a few dozen Einstein rings known, but not a large number.
So then the follow-up question to that is, how useful are gravitational lenses for observing distant objects? Is it really possible to reconstruct the original object from the image, or are gravitational lenses mostly too complicated for that to ever really be possible?
No, gravitational lenses are very useful in extragalactic astronomy because they're essentially gravitational optics experiments. And just like an optics experiment in the lab with light, you can model the light distribution, the sea, and how the light was bent to make a model of the object during the lensing. And so they're very useful because each gravitational lensing experiment leads to a model of the mass distribution of the object causing the lensing. Typically, it's a galaxy. Typically, most of its mass is dark matter. And that means lensing gives you a handle on how much dark matter is in a galaxy or sometimes a cluster of galaxies. And it also gives you a little indirect information on the distribution of that dark matter. So we've learned a lot from the few hundred examples we have of gravitational lensing because of this.
The next question is from Papasta Pastor. Sounds Italian. Good morning. What could be the potential ramifications of finding carbon-based microorganisms or fossils on Mars? How would science and theories be affected?
Well, the search for life on Mars, whether it's existing life, and that's going to be hard because it will be on almost certainly fairly far underground, tens of meters, and we can't probe those depths with any instrument that's planned or current, or past life on Mars, which would be profound in astronomy. So the detection of life on Mars, fossilized life forms, or present day life forms, would be a second genesis. And if that life has a similar biochemical basis to the Earth, that at some level indicates that there's a universal biochemistry. The hesitation, of course, is the fact that rocks can travel from the Earth to Mars and vice versa, because impacts occur and the life-bearing rock could travel through interplanetary space and reach the other planet. It's easier for a rock to go from Mars to the Earth than the other way around. So it's more likely that life on Mars seeded life on Earth and the other way around, but it can go in both directions. If the life on Mars does not have the same biochemical basis as life on Earth, in a sense, it's more exciting because it means that we have a second variation, we have a second genesis, we have an independent model of biochemistry, not the same as ours. And as soon as you have two in just one solar system, the odds are in the universe, you're going to have many, many. So in a sense, for biologists, it would be more exciting to find life on Mars that is not like life on Earth.
Thank you very much. The next question is from Yangip, who has a question about carbon and life. So is there a way in astrobiology to think about the development of life that's not Darwinian? Darwinian changes seem to be more for like animals and large scale organisms. Is there another way of thinking about this development for astrobiology?
Right. It's a good question. So we don't know. Astrobiology is a young subject. We don't have any other examples of life beyond Earth, so we're speculating. The speculation, however, is that if life reaches advanced states beyond the Earth, it will be subject to some form of natural selection, the way that Darwin described for life on Earth, because all that really is saying is that biology is molded and responds to the environment. It uses the energy sources that are available. It uses the physical conditions that are available, and it has to survive and replicate and reproduce and evolve in those environments. And that could be a universal process. So we imagine that some form of Darwinian natural selection will operate on advanced life forms elsewhere, but we don't know. There's even a variation of natural selection that applies at a much more simple level. The evolution from simple chemical systems to biological systems also involved some form of selection because you had to select molecules that were more active. You had to select molecules that were able to store information, leading to RNA and DNA. So there's a form of sort of chemical natural selection that leads to biochemistry that we also don't understand very well how it happened. But that's a sort of an even more primitive form of natural selection that we also think operates in places beyond the Earth.
The next question is from Pargade1. Would you please explain what adaptive optics is and how it is used to get sharper images from telescopes?
Yes, adaptive optics is a very powerful method that has matured in astronomy in the last 2 decades. Experiments in adaptive optics have been going on for a long time, 30 or 40 years, but the technology has only matured in the last 10 or 15 years. And now it's so mature and successful that it's used essentially on every modern large telescope, and the ones that are being built in the future. It's a way of solving a big problem with optical telescopes on the ground or infrared telescopes, which is the blurring due to the Earth's atmosphere. So no large telescope on the Earth's surface can achieve the resolution that is available to it from its optics, the diffraction limit of its mirror or its lens, because of the blurring of the atmosphere. Adaptive optics uses very clever techniques to correct for the distortions for the atmosphere. Usually that's not by altering the shape of the primary mirror, because that's usually a large and rigid object, but it's usually done with a secondary mirror, which is made of a thin shell with piezoelectric actuators, which can adjust its shape and surface dozens of times a second, and essentially use that to counteract the variations in the wavefront that arrives through the Earth's atmosphere. So variations, turbulent motions in the atmosphere, variations in temperature and density, mean that a plane wavefront arriving through the vacuum of space is distorted into a wavy or undulating wavefront. And that wavefront changes many times a second due to the churning atmosphere. Adaptive optics makes corrections for that in real time and reproduces, in the ideal case, the diffraction limit of your telescope. So it's a huge gain on what you would have without adaptive optics.
The next question is from Mountain of Pillows, and then this question I think can be interpreted in two ways. So I'll ask it in one way, and then we can look at it in another way. Is there any sense to the type of multiverse where, with space being infinite and there being less than infinite ways matter can be configured, that there could be somewhere else in space, in real space, where an exact copy of us can be found somewhere else in the universe?
In the theory of the multiverse, which is a speculative theory of cosmology, but it's being explored by theorists and has been for a few decades, yes, it's possible that if space-time fundamentally is infinite, then the expanding universe and space-time we occupy is not the only space-time. And once you have other possible expanding space-times with slightly different properties, then you have the possibility variations on the theme of our universe. And of course, if space-time is infinite, then you essentially have infinite number of experiments. And so you have the actual probability that in some location, some distant region, what happened in our universe has been replicated down to the level of an individual person or object or civilization or planet. That's very speculative, but it's logically a possibility.
So then the other sense of the multiverse, like, for example, in Marvel, is this some sort of quantum mechanical idea that at every decision point, the universe splits off into a multitude of sort of versions? Can you talk about how that idea came to pass, and if what the possibilities are for that?
So that version of the idea tends to be called the rather than the multiverse, it's called the sort of many worlds theory. And so that's the standard term for that. And it emerged from quantum theory. So as people were considering the quantum probabilities that are embedded in quantum theory, our microscopic theory of nature, where atoms do not have, fixed certain probabilities, but they have space distributions and probability distributions and probabilities of different outcomes, then the many worlds theory, and it would emerge from the brain and the ingenuity of a man called Hugh Everett, I think in the 1930s, a physicist. So it's really his idea, was that rather than having probabilities of outcomes in our universe, each possible outcome, each possible situation actually occurs and is the case in a series of branching probabilities. And so you have the universe endlessly bifurcating and bifurcating again into other universes where a particular outcome has happened, and you don't have to deal with a probability distribution. So if you do the many worlds theory, it's a way of sort of finessing the probability or the probabilistic aspect of quantum theory and creating certainty in a manifold of universes that become, of course, almost infinite in the end. So it's sort of a sleight of hand, if you like, and it's a philosophical idea. It's been treated as such. It hasn't had a lot of work on it in the last half century or so because it's not necessarily a fruitful hypothesis for physicists or for astronomers. but it has logical validity. And so it's part of the history of thinking about quantum theory and of thinking about cosmology.
Excellent. Thank you. All right. We have time for one final question, and then we have to let Chris go to another event. Jim McLeod asks, in the images of M87 and the Milky Way's black holes, the dark areas are sometimes described as a shadow rather than the zone contained within the event horizon. Can you explain how the shadows we see around us in the world are somehow analogous to a black hole shadow in those photographs?
Yes, I think shadow is not technically the best term for what you see in those images of the black holes, the two mentioned, the Milky Way and the M87 black hole. A silhouette may be a better way of putting it, because you have a dark object. Dark object is the black hole. It's surrounded by bright material. The bright material is the accretion disk. And of course, what's happening that makes it very different from a shadow. So just to remind us of what a shadow is when you have an illumination and there's an obstruction or obstacle, and the shadow is cast around or by the obstacle with light traveling in straight lines. But that's not the situation in a black hole, because in the black hole is indeed dark, but light is being bent around the black hole. In other words, you're seeing right around behind the black hole. So that's very different from a shadow in linear optics and in everyday life. So I think silhouette is a slightly better term for it, but the truth is that when you're talking about light that is traveling on curved paths, none of the words that we associate with conventional optics of everyday life are completely suitable. You actually just have to think of the real situation of the curved path of the light around a truly dark object. That's a good question to end with, and I appreciate the variety today, as always. I think we have another time set aside while I'm still on my travels for a live session. I can't remember if it's 2 weeks from now, but Matthew will say or will remember, and we'll be back with you then.
Excellent. Thank you for your time today, Chris. Yes, the next one will be September 20th. Also at the same time, 8 o'clock for Tucson. Chris, have a great time, and we will see all of you in 2 weeks. That will be on YouTube.
Okay. Thank you, everyone. And thanks to Matthew and Vicky for running the session.